Okay, moving past that model to now help you recall the quantum theory behind the atom. We also know that the electron behaves in certain cases by experiment as well, just like a wave. So we have wave-like properties to the electron with quantized energy. Okay. And so we often use probability distributions to calculate the sort of volume and shape and size of the orbital that is the three-dimensional wave about the center point of an atom and its energy. With that, we're able to take these probability functions and generate three-dimensional views of what the 3D wave of an electron centered about the nucleus of an atom might look like. So the 1s orbital, we saw that in the previous planetary model where 2 electrons on carbon reside, is a spherical orbital where the nucleus is at the center of that sphere. We also saw in the carbon atom that there were 2 2s electrons and 2 2p electrons. So in the case of the 2 electrons that are associated with a 2s orbital, a larger sphere is what's shown for the three-dimensional wave function of the electrons. And again, the nucleus would be centered about this three-dimensional space generated by the probability distribution. As we continue the trend, 3s electrons, again, a sphere is had there, 4s, an even larger sphere for that orbital for the electron. Okay, so in review further, we see that each orbital has a unique shape and orientation and probability distribution, and our principal quantum numbers give us some quote-unquote coordinates to help us reflect this uniqueness to each orbital. And the energy of each of these orbitals can be set on an energy scale. So here's an energy scale here. And you can see that the lowest energy orbital is the 1s orbital. This is where most of the electron density is located closest to the nucleus as reflected in our diagram over here. Sort of next best, the next lowest energy situation for electrons in their orbital situation is the 2s orbital. And here you can see, because the size is a little different, the electrons reside a little further from the positive nucleus, and therefore the energy is a little bit higher on this energy scale. So that is, the electrons in the 2s orbital would be a little bit easier to remove because they're higher in energy and located, quote unquote, further from the nucleus. And so most orbitals lie on an increasing kind of energy scale as such, and at first glance it can be a bit difficult to predict the order in which all these orbitals locate, but the periodic table helps us understand the order of this. So we'll see that in a moment. The 2p orbitals are shown here. Okay, so notice that 2p orbitals have kind of a dumbbell type shape where there's a positive and a negative phase to that dumbbell. That has consequences on how we make covalent bonds. We need to overlap positive phases with positive phases to make a covalent bond. And same thing occurs for the other two orientations of these p orbitals. So we have generally a px, a py, and a pz or z option here. All that can be found in either principal quantum number 2, 3, 4, 5, 6, etc. for the atom. Note that there is no 1p orbital. The 3d orbitals are the next type, so we only see them starting with principal quantum number 3, and there are 5 options there. They look like double dumbbells, again, where there can be positive and negative phases to these orbitals. And they're rotated again throughout the Cartesian coordinate systems for many of the options. So here you can see a dx, a dy, and a dz configuration, and then a dx minus y squared, and even a dz squared are the two less more unusual options where we've now rotated them sort of differently. Certainly the last one is a different format entirely. Okay, so some takeaways here are that each of these sort of three-dimensional waves or orbitals for the electron modeled as a wave can hold or accommodate two electrons. Okay, so we can see here that in our previous carbon model, we knew that two electrons were located in the 1s orbital, so that we can see how they would be symmetric in their wave as far as shape and distance from the nucleus, and that there were another two in the 2s, so a little further from the nucleus, and we would expect that the 2p options for our final two electrons in the carbon atom would be in these p orbitals, or a dumbbell type shape, if we put the Cartesian coordinates at the center of the nucleus. So we can use these predictions to describe the likely electron behavior based on electron energy and the configuration. Okay.